It is part 2 of the project Canny Edge Detection for Color Images. The first part introduced the Canny Edge Detection algorithm. The algorithm has 5 steps. And here we'll begin considering details of each step and try to find new ideas for a better edge detection algorithm. Here is the first step, noise reduction, image blur. This step can be done by applying the Gaussian filter. This im Gauss filter is a built-in function. You can use it quite easily. It is a simple averaging algorithm and blurs the whole image, and without distinguishing edges and non-edge pixels. So it can make edge strength weaker. So we'll try another method. Here, we'll try the total variation model, TV model. It is given in this PD equation. If you are not familiar with PD, then just listen to me and try to understand the core idea of this model. Here, this is the mean curvature, and beta is a constraint parameter, which is a kind of a Lagrange multiplier. And we'll study the details of Lagrange multiplier techniques in section 30.A. Here is the major property of the TV model. The TV model tends to converge to a piecewise constant image. Such a phenomenon is called the staircasing effect. So the TV model can be used for both noise reduction and simultaneously edge sharpening. So it can be used very effectively for the noise reduction without making edges weaker. And we have to discretize the PD equation to get approximated the solution. And we may apply simple exploration method, which is the Ford-Euler method here in nth level, and we try to get the new level n plus first level solution by solving that equation. So here, move distance to right side and multiply delta t, and move distance to right side, we can get that one. Now, this term is approximated as AUN. Here, AUN is approximation, in fact, numerical realization of the negative, the curvature, so that by taking some iterations using that equation, we can get denoise the algorithm. The TV model and P-point 1.3 requires to set delta t small enough for stability. That means that you have to choose delta t quite small. If you choose large delta t, then it will not work. The solution will blow up. You can reduce noise effectively in a few iterations. Implementation details can be found from TV denoising.m and the curvature pg.m in the packaging, in the model code packaging. Here we'll compare the performance of two methods for the LENA image, and we try to denoise component wisely. For each channel, we apply TV denoising and also Gaussian filter and we saved into UT and UG respectively, and we here save the final image, and here we see the result. And this is original Lena image, and this is TV denoised image, and that one is Gaussian filtered image. As you can see from this mid picture, the TV is reducing the error and preserve the edges. Yeah, for example, around here, and these are a little bit oscillatory. Now these small oscillations almost disappeared. And however, edges are well preserved. For Gaussian filter, now every blurry, if we choose sigma smaller, for example 1, then you can get less blurry image. However, in any case, you have to be a little bit careful when you are using Gaussian filter. It blurs everywhere. Now we have the second step of the Canny edge detection algorithm. Gradient calculation, Sobel gradient. Edges correspond to a change of pixels intensity. To detect it, the easiest way is to apply filters that highlight the intensity change in both directions, horizontal direction and the vertical direction. Here we have algorithm for Sobel gradient. Sobel gradient is a computational algorithm for gradient, x directional derivative and y directional derivative, and by using convolution with so-called Sobel kernels. Here we have Sobel kernels in x direction and y direction. Let's see what they are. Here we consider pixels. Okay. Rather than pixels, let's assume that the image values are saved at each grid point. So for this point, now the weight 1 here, weight -1 means that this value minus this one, and that is here representing slope in horizontal direction. And once the length of a pixel is 1, then this value minus this one divided by 2 must be used. However, it is a kind of a scaling problem, the scaling, so that we ignore the divided by 2. So this value minus this one is representing u sub x, x direction derivative. Rather than one evaluation, we evaluate here, 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 3 horizontal slopes, and we make weighted average here, twice of this one, and once and once. That is exactly this one. Yeah, that slope twice, and slope, slope. And we have to also divide by 4, and because of 4 contribution, but it is again scaling, so we ignore. And so this, along with that filter here, and along with the image, and you apply convolution with the filter, then you will get here u sub x. That is an approximation of x directional derivative. And for ky, the similar you can consider that here that's 1 and -1, then it's representing y directional derivative, and here measure 3 of that slope, and then 1 to 1 weighted average here, and with that filter and by applying convolution operator, you can get U sub y. That's how the sovereign gradient is measured. Okay, and after getting it, just this length is the magnitude, and here arctangent of U sub y over U sub x, that is angle. So this angle represents the normal direction of the edge. Once edge is now running that way, then that normal direction is that theta direction. And in MATLAB, Etan 2 is built in, and you can use in this way. Okay. So implementation detail will be found in Sobel grad.m, and also you'll see on the next page. Okay, here. Okay, now in the program, the color h.m, the gradient magnitude is saved in E0, and then it is normalized, but you don't need to normalize the value, but normalization is done only for the purpose of figuring. So we try to make the value maximum value is 1, and that is the double precision, the image value, the maximum value is 1, so that we normalize it in this way. So in figuring, you can make quite conveniently the figure of the gradient magnitude profile. Okay, here, if we try to get information about Etan 2, then by using help comment, you can see that. Then part of output is given in this way. Etan 2 yx is the 4-quadrant arctangent of the elements of x and y, such that the result is between minus pi to pi. That means that it's measuring the arctangent so that in the coordinates, and here now, here from minus pi to pi is measured. Okay, so output value has some portion minus pi. That means that, for example, this angle, then it is directing this direction. If you add pi, then it will here direct the direction will be the opposite direction if it is pi is added. But in our computation, either this direction or that direction, it doesn't matter. It can be the magnitude. In the beginning, the magnitude over there, angle is measured by using U sub y and U sub x, but the magnitude is just contributed as a non-negative number, so that if you are using here partly non-negative number, then it can be changed into that way, so no problem. Okay? But anyway, the output is minus pi to pi. Okay, here this is Sobel grad.m. Okay, so your output is gradient profile, and then here angle. Now, as you can see here now, for instance, ux is measured in this way for each point. Now, and we are using index p and q that is in the vertical direction, there is horizontal direction, and qm is left point of q, qp is right point of q. And now for pm, that is now in fact Okay, that is lower point, upper point, because it is a vertical direction. This is now left point, right point. However, if it becomes 0, then rather than 0, we are using 1. If it is larger than m, then we are using m. So by using maximum and mean, it is a little bit adjusted. But main idea is Pm is now P less than 1 if it is not hitting the boundary, and PP is P plus 1 if it is not hitting the boundary. The same way M and P are used. So here for UX, now, okay, PP and PM, so that is first component, and then QM, and lower horizontal difference, and now the central difference, horizontal difference, and that is now upper, there's a P and P, so the upper horizontal difference and weighted, 1 to 1 weighted, and also similarly for UI it is computed, and now here the square root of UX squared plus UI squared is saved into gradient magnitude, and now theta angle is saved from the result of now atom 2 UI and UX. Okay, that's the Sobel gradient, and after getting it, we try to see the magnitude of each of the RGB component. Yeah, there's RGB, and apparently the G green component has the largest magnitude. Right? And however, the pink component has also around there some of details. Okay, so this is magnitude of RGB gradient components for the LENA image. Okay. Now, through the project, we may get the single component gradient by simply taking the maximum of RGB gradient. So out of these 3 gradients, just we try to take maximum value, then we can see this one. Okay. Now, so here we are trying to get the gradient, the channel by channel, and after that we try to get a single value the gradient. In this case, maybe we can use some other technique rather than taking maximum, and we can get really much better algorithm. For example, in part 1, this color checkerboard image, if it is transformed into grayscale, then except these 2 blocks, every else same gray value, so that the conventional method can detect only these 2 blocks and edges of these 2. And however, if you are dealing with the channel by channel gradient and try to get one single valued gradient out of that, then you can get such kind of gradient profile. In this case, we are choosing maximum of its RGB, the gradient components, but here is reasonably good. So here we can get more reliable edges. So that is the major benefit and major advantage and over the first, the classical transformation kind of algorithms. Okay, that's the part 2, and we'll continue in part 3 and also step 3, step 4, step 5 will be explained. Okay, thank you.